Hi kiddos, it's Mr. Spear again. We're back giving an example here with ratios of areas. And this example that I wanted to show you guys combines a couple of the methods that we talked about when comparing those. So let's quickly just do a quick reminder of what I was mentioning before. The first thing that I wanted to mention here was that you can have an example where you have similar figures. So if you have similar figures, then you're going to be doing this a squared to b squared stuff when you're comparing the areas. But the other thing that can possibly happen here is, and I'll put that over here, is you can also have triangles that have the same height or the same base. And if that's the case, then basically the ratio of their areas is going to be the ratio of the differing piece, whether that's the height or the base. So let's go over a couple examples inside this problem and see if it makes sense to you. All right, first things first. We're going to begin by comparing the ratios of triangles 1 and 3. And the only thing we're given here is that this is a trapezoid. So we know that the top and the bottom lines are parallel, and I'm going to know that the top side is 8, the bottom side is 18. So we want to compare these triangles here. I'm going to go and highlight them. All right, this triangle on top, triangle 1, and this triangle here on the bottom, triangle 3. Okay, so what do we know about them? Well, we're going to know that they're similar. So I'm going to go ahead and write up here, these are similar figures. Well, how do you know that? Well, because this is a trapezoid, the top and the bottom are parallel, which means that this angle right here and this angle right here are going to be the same because of their alternate interior angles. If the lines are parallel, then the alternate interior angles are the same. Same thing for this angle and this angle here. And to top it off, we also have two vertical angles here, so those are going to be the same. All right, so we know they're similar figures. Once we know they're similar figures, then the next question is, well, what's their scale factor? What is their A to B here? So I'm going to go ahead and I'll put a little teeny, I'll mark it up here. What is their A to B? So, well, it's going to be 8 to 18. That's how big those distances are. We're going to simplify that just a little bit. Let's divide it by 2. I'm going to get 4 to 9. Now what that means is that their A squared to B squared, if I square those, I'm going to get 16. Do a different color here. We're going to get 16 here, and when I square 9, I'm going to get 81. That's how much area this has compared to the other one. So I'm going to go ahead and highlight this one here. So let's go ahead and fill this one out. So I know that this is 16 to 81. Okay. What about this next situation here? Now we're going to be looking at the following triangles. We're going to be comparing 1 and 2. All right, so 1 is right here, and 2 is right next to it, this one right here. Okay, so I want to compare the areas for those triangles, and what situation is that? Well, that situation is going to be different, and the reason that it's different is because both of these triangles, and I'm going to ask you to think about this being the ground, and I want you to think about how tall are both of those triangles. Well, hopefully it makes sense that both of those triangles are exactly the same height. And because they have the same height, and I'll put it over here, they have the same height, which means that their actual, let me go ahead and erase this piece on the bottom here. That means that if you're looking at the ratio of their areas, all you got to look at is, well, what is this differing base to this one? That's going to be the ratio of the areas. Well, how do you get that? Well, remember, we already learned that these triangles are going to be having, and I'm going to go and highlight the top one to make this a little more clear. You remember this top one and the bottom triangle here? We said they were similar, and we said that because they're similar, their lengths are going to be in a ratio of 4 to 9. I'm going to go ahead and put this little piece here, 4 to 9. That means that so this base right here and this piece right here, they're in a ratio of 4 to 9. And because that's true, their areas are also going to be in a ratio of 4 to 9. 4 to 9. And because they have the same height, right here, you know that their areas are going to be in the ratio of whatever's different. And because their bases are different and the bases are 4 to 9, that means their areas are 4 to 9 as well. The same basic thing is going to be happening here, and I'm going to try to highlight this one. We're looking at triangles 1 and 4 now, and those are also, and I'm going to draw it here, 1 and 4 also have the exact same height. And because they have the same height here again, then you're going to ask the question, well, what's different about them? If they have the same height, the only thing that's different about them is going to be the base. And the base, again, is in that ratio of 4 to 9. So you're going to also know that their areas are 4 to 9. Okay. So what's next? The next thing we want to compare is going to be triangles 2 and 4. So if you want to compare triangles 2 and 4, then what you're going to want to do is you're going to see that the triangle 1 to triangle 2 was in a ratio of 4 to 9. I'm going to go ahead and let me put this in red, make it a little easier here. The area of this one was 4 to 9, and the ratio of areas of 1 to 4 is also 4 to 9. So they're both exactly the same size compared to triangle 1, which means if you're comparing triangle 2 and triangle 4, they're going to be the exact same size. So we're going to say those are 1 to 1. Okay, now the last piece of this is a teeny bit confusing, but think about this. What's the area of triangle 1 compared to triangle 3? We said 16 to 81. What's the area of triangle 1 to triangle 2? Well, we said 4 to 9, right here and here. Okay, well, those aren't the same relative measures. You see how we have 16 to 81 here, but we have 4 to 9 here. So one of the things that I'm going to do right now, I want to make them all the same relative measure compared to each other. So what I'm going to do is I'm going to say, well, how big is, if triangle 1 is 16, then how big would triangle 2 be? So I'm going to kind of quadruple everything. Instead of this 4 right here, I'm going to quadruple it to 16, which means that this side, or this triangle, is going to be 36. This triangle is going to be 36 as well. So that now they're all the same relative areas compared to each other. So the last question that they're going to ask is, what is, sorry about that. The last question they're going to ask is, what is the area of triangle 1 to the entire trapezoid? So basically what I'm going to do at this point is I'm just going to add up all the areas here, this top one here, and we're going to say triangle 1 was 16, triangle 2 was 36, triangle 3 was 81, and triangle 4 was 36. I'm going to add all those up together, and I'm going to end up getting 169. That's what all the different triangle areas are going to end up with. We already know from the beginning that triangle 1 had a ratio of 16 here. So we're going to get that the ratio for 1 to the entire trapezoid is 16 to 169. So this kind of combined not just similar figures, but also that other idea with triangles that have the same height and or the same base. All right, thanks guys.